All right, so this is number 16, and the title is Mapping Onto Itself. So a line of symmetry, that's our first topic for today. Line of symmetry is a line of reflection. So this kind of relates to what we did yesterday and the day before where we were reflecting things. But it's not just a regular old line of reflection, it's a special type of line of reflection. It's a line of reflection that goes through a figure. So that's different, right? Because those lines of reflections we were looking at before, the figure was way over here, and then it reflected way across the line. So this is a special type of line of reflection that actually goes through the figure and cuts it exactly in half. A line of symmetry is a line of reflection that goes through a figure and cuts it exactly in half. So now that we have the words, let's see a picture. Like it could look like this. Make sure I get my picture good here. And then if you drew a line here, that goes through the figure. And if you reflect this over to here, it'll match up. And if you reflect this over to here, it'll match up. And so that's called a line of symmetry. So it's a special type of line of reflection that goes through the figure. Okay, then the other concept for today is rotational symmetry. And a figure has this. It has rotational symmetry. If it can be rotated about its center and match up with itself. A figure has this if it can be rotated about its center and match up with itself. Okay, so what that would look like is, if you had a figure like this, and here's the center. And then what you can do is, if you just, so here you're going to rotate it around the center, about the center. And what you can do is if you just take this and rotate it to there, then the whole figure will be back where it started, basically. It'll be the same as what it was. Or if you rotated this to there, it would also match up with itself. So that figure over there has rotational symmetry because if you rotate around its center, you can match it up with itself. It also has line symmetry as well, but that's not what we're talking about right now. So line symmetry is when you can reflect across and match up, and rotational symmetry is when you can rotate and match up. Okay, so that's all for the note card today. I'll pass out the hole punch. And you need a sheet of paper. All right, so the title of the paper is also mapping onto itself. And there's kind of a weird looking figure in number 1. So it starts out like this. It's a parallelogram, a little tiny one. So I do need you to draw this, please. So there's a little parallelogram. And then there's another one over here, going the other way. So parallelogram, and then another one next to it, slanting the other way. Kind of tricky to draw. And then there's a diamond on top of it. It's the Mitsubishi logo. So it's easier to draw if you just do it piece by piece. Parallelogram, then another parallelogram, and then a diamond on top. Okay, so the question says, does this figure have line symmetry? So the question is, can you draw a line of reflection through it and then have it match up with itself when you reflect across it? The answer is yes. Okay, so yes, it does have line symmetry. And then it says, if so, draw the lines of symmetry. So here's one of them. So if you reflect across to there and across to there, it's going to match up with itself. But there's another one here. If you reflect down to there and reflect up to there, it also matches up with itself. And there's a third one here. So this figure has 3 lines of symmetry. So some of the questions say, if it does have line symmetry, say how many lines of symmetry there are. If it said that, you'd say 3 on this one. But this one says draw the lines, so we just drew in the dotted lines. Okay. Hey. Okay. Right on. They kept it safe for you. They kept it safe for you. Okay, here's the next figure. This one's a little bit easier to draw. So the question again is, does this have line symmetry? What do you think? Doesn't. I mean, you could draw a line in here, but then if you reflect it, this piece would be going up, so it wouldn't match up. And this piece reflected across would be going down. So it doesn't work out. Don't draw that line, because you're only supposed to draw lines if it has lines of symmetry. I was just trying to explain that that one wouldn't work. Okay. So the next one's a hexagon. Still the question is, does this have line symmetry? And the answer is yes, it does. So we have to draw in the lines. So there's one here. Then there's one here. And here's a third one. Here's a fourth one. Fifth one. And a sixth one. From all the corners to the corners, and from all the middles to the middles. So if the question said, how many lines of symmetry does it have, you'd have to say 6 for this one. Okay, now the question changes. So here's the figure on number 4. This time the question is, does this figure have rotational symmetry? So that means you got to put a dot in the center and picture it rotating around there. So if you rotate this one around, is it possible that it's going to match up with itself as you rotate it? Yes, so this has rotational symmetry, good. And then it says, if it does have rotational symmetry, find the angle of rotation. So I'm going to draw in this line here. And if I rotated that to there, then it would end up matching up. So this angle in here, that's called the angle of rotation. It's how far you rotate to get from there to there. And so I have to figure out how many degrees that is. So if you rotate all the way around, that's 360. And this is 1/3 of that, because 1, 2, 3. So to figure out how many degrees that is, we're just going to take 360 divided by 3. So the angle of rotation is 120 degrees. Okay, here's the next figure. So the question again is, does this figure have rotational symmetry? So I put a dot in the middle. And then you picture it rotating around itself. And it would never match up, right? You could turn it partially, and then it would be the curve on the side. You could turn it again, and then the curve would be on the bottom, and then the curve would be on that side. But it's not going to match up again until you go all the way around. So this one doesn't have rotational symmetry. It does have line symmetry. But that's not what the question's asking. It's asking for rotational symmetry. Okay, still the question on the table is, does this have rotational symmetry? So what do you think? This one's harder for people to see. So if I rotated it a fourth of the way, it would end up looking like this, right? So it's not matching up. But if I turn it around halfway, then it would match up. So if I took this and rotated it all the way to there, then it would match up. Okay, so this is yes, it does have rotational symmetry. And all the way around is 360. So half the way around is 180. So on this one, the angle of rotation is 180 degrees. Because if you turned it from here, from here to here, half the way around, then it would match up with itself. So that one's a little bit tricky for people. Okay, now we've got some true-false questions. Two true-false questions. The thing that you have to remember about true-false is, in math class, to be true, it has to always be true. Okay, so here's the first one. You don't have to write this down. A line of symmetry is a line of reflection. So this statement says a line of symmetry is a line of reflection. True. So Charlie's saying true. So let's think about this. If we've got a line of symmetry, here's a line of symmetry. Is this line of symmetry also a line of reflection? Yeah, because if you reflect across it, it's going to match up, right? Is every line of symmetry a line of reflection? So, Jennifer, give me an example of a line of symmetry that's not a line of reflection. Okay, good. So she's thinking from yesterday we had like a triangle reflected across here. This is a line of reflection, but it's not a line of symmetry. So it's not possible to find a line of symmetry that isn't a line of reflection. Because the subject of the sentence over there is a line of symmetry. So every picture has to have a symmetry line in it. So this picture doesn't qualify, the one you were thinking about, because this isn't a line of symmetry. Okay, so every line of symmetry is also going to be a line of reflection. This is true. That's because a line of symmetry is a special type of line of reflection. Okay, so every line of symmetry is a line of reflection. That's true. Okay, but now I'm going to turn that around and say, so this is another true-false question. You don't have to write down. So for number 7, all you had to do was think with me and then write true. Okay. So, okay, so number 8 says a line of reflection is a line of symmetry. So in this one, the subject is line of reflection. So all of our pictures have to have reflection lines in them. Okay, so here's a reflection line that is a line of symmetry, right? Here's a reflection line that's not a line of symmetry. So that means this statement is sometimes true, some lines of reflection are lines of symmetry, and sometimes false, because some lines of reflection are not lines of symmetry. And in math class, if it's sometimes true, sometimes false, then we say it's false. Okay, so this is a false statement because not all lines of reflection are lines of symmetry. This was a true statement because all lines of symmetry are lines of reflection. Okay, good. So those are very subtly different. Is everybody okay? All right. Next one is number 9. And this is the last one I'm going to help you with. Thanks for paying attention, even on a Friday. I appreciate it. Okay, for number 9, we need to plot some points. So you need a y-axis and an x-axis. And do the best you can with the spacing. Try to get it evenly spaced. So the farthest you have to go is 1218. So this point is point B. It's 1218. And there's also a point A, it's 8,6. Bless you. So point B is 1218, and point A is 8,6. Okay, then these are the pre-image points, right? Because they don't have any tick marks on them, so they're pre-image. Then there are also image points. A prime is 10,2. So here's the pre-image point, here's the image point. So I guess this is a transformation, because I've got pre-image and image. And then B prime is 1414. Just do the best you can on the spacing. You might not get it perfect, that's okay. Okay, so I got A, the pre-image is 8,6, A prime is 10,2, B is 1218, B prime is 1414. So we got pre-image image, pre-image image for two different points. Yes? Just, okay. Well, what is the question? What is the question?
Would the question be figuring out what x plus or x plus or minus plus or minus a number?
Okay, I know what you're thinking. So what Charlie's thinking is he knows this is a transformation, right? Because we've got pre-image and image. And he's thinking it's a translation. Because he's saying, I got to figure out how to get from there to there and how to get from there to there, right?
Yeah.
He's saying, I got to subtract so much and add so much. That's a good thought in his point. You see what he's saying? is this a translation? Like he's thinking. How could we tell? Like, how do points move in a translation? Yeah. Same distance and same direction, right? Is it the same direction? Yeah, it's looking that way. Is it the same distance? No, that one's bigger. B to B prime is larger than A to A prime. So it's not a translation. So Charlie, that was a really good thought. But the reason it's not a translation is because these points are not moving the same distance. Okay, so what must it be if it's not a translation? A reflection, right? Because that's the only one we've had. Okay, so this is a reflection, and we're going to try to find the line of reflection. That's what the directions say. Find the line of reflection. You don't have to write this down. I'm just making sure we're all with me. Okay, so we're just going to sketch it in. It looks like it's about right here. So there's the line of reflection. And we're going to find out what it is exactly. So I'm going to draw in the connector line and the other connector line. Okay, what do we know about lines of reflection and connector lines? Yeah.
The lines of reflection intersect the midpoints of the connector.
Awesome. This is a midpoint. This is a midpoint. What else do we know about lines of reflection? They go through the midpoints, and they're perpendicular. They're supposed to be 90s, 90-degree angles. Okay, so that's two things we know about lines of reflection compared to connector lines. They go through the midpoint of the connector lines, and they make a right angle with the connector lines. Okay, so in order to find this, I can find a point that's on the line by doing the midpoint. So that's 8 plus 10 divided by 2. And 6 plus 2 divided by 2. So I'm doing midpoint formula because I know that the line of reflection goes through the middle. (18 divided by 2 is 9. 8 divided by 2 is 4. So that tells me that point right there is 9, 4. Okay, then also I'm going to find the slope here to find out how these points are moving. The slant. So that's 2 minus 6 over 10 minus 8. I don't need parentheses. Two minus 6 is negative 4. 10 minus 8 is 2. So the slant is negative 2. Okay, how do slants of lines compare to slants of perpendicular lines? It's been a while since we talked about this. How does the slant of this compare to the slant of that, if it's perpendicular? Yes?
Is it opposite and reciprocal?
It's opposite and reciprocal. And reciprocal is a fancy word. I'm glad you used it, but reciprocal means flipped. So if I want to know the slant of this line, I need to do the flipped opposite of this. If I want it to be a fraction, I can put it over 1, right? That's the way I can force it to be a fraction. So the flip is 1/2, and the opposite is positive 1/2. Okay, so the perpendicular slope is positive 1/2. We figured out the slant of this line was -2, and then we can flip opposite it to figure out that the slant of this line is 1/2. Okay, so if we want to find this dotted line, the line of reflection, we use the point that it goes through, which is 9,4, and the slope that it goes through. Okay, to find the equation of a line, you do y equals mx plus b. That's the template. And the slope is 1/2. So I know the slope of my dotted line is 1/2. That's why I'm putting 1/2 in for m. Okay, then to find the b, I use the point. I put 9 in for x and 4 in for y. So 9 for x, 4 for y. Is everybody doing okay? I know it's hard to pay attention to this for a long time on a Friday. So if I lost you, I won't be mad at you, just tell me. Okay, so now 1/2 times 9 is 4.5. And then you subtract 4.5. So that means the y-intercept is -1/2. So final answer for the line is y equals 1/2 x minus 0.5. And that means my picture's off. Like apparently this line is supposed to like hit at -1/2 on the y-axis, right? So I didn't get everything spaced right, apparently. Technically this line is supposed to hit the y-axis at -1/2. Maybe you did better, I don't know. You can see. All right.